Today, we are diving into one of the biggest, most mind-bending mysteries in all of physics. It's a story about a tiny, almost insignificant flaw in the laws of nature, a concept called CP violation that, it turns out, is the very reason you and I and everything else exists at all. So it all starts with this massive cosmic puzzle. Our best theory, the Big Bang, tells us that the universe should have created matter and its weird twin, antimatter, in perfectly equal amounts. But here's the catch. If that happened, they would have instantly wiped each other out in a huge flash of energy, leaving behind, well, nothing, an empty void. So the question is, why are we here? Why is our universe brimming with galaxies and stars and us, instead of just being empty space? To even begin to answer that, physicists had to question one of their most basic assumptions, the idea that the universe is perfectly symmetrical. For a long time, they thought certain laws were just unbreakable, that nature didn't play favorites. You could think of it like a perfect mirror, where the reflection is always a flawless, exact copy. Now, there are two key symmetries we need to talk about here. The first one is charge conjugation, or just C. That's basically swapping a particle with its antimatter twin. The second is parity, or P, which is like flipping the entire universe into its mirror image. For decades, the thinking was that the laws of physics should work exactly the same in either of these scenarios. By the early 1960s, scientists had discovered that okay, maybe C and P could be broken on their own in some weird specific cases. But, and this is a big but, they were absolutely convinced that the combined symmetry, C and P together, was always conserved. This was treated as a fundamental, unbreakable law of how everything worked. So where did the first crack in this perfect mirror appear? Well, it came from a very strange place, a teeny tiny subatomic particle called the neutral kaon. And this little particle, it didn't seem to play by the rules. You see, kaons are just weird. A neutral kaon isn't just one single thing. Thanks to the bizarre world of quantum mechanics, it actually exists as a strange mix of two totally different states at the same time. We call them K1 and K2. And each one was expected to behave in a very specific way. These were the established rules of the game. The K1 state, nicknamed K short, had a positive CP value and was supposed to decay super fast into two particles called pions. The K2 state, or K long, had a negative CP value and was supposed to decay into three pions, which took a lot longer. And here's the crucial part. A K long particle decaying into two pions, that was considered strictly forbidden. Impossible. Right, so everyone thought they knew how this worked. But in 1964, two physicists, James Cronin and Val Fitch, decided to build an experiment to really put this so-called unbreakable law to the ultimate test. Their entire experiment was built around this one simple idea. If CP symmetry is a real, perfect law of nature, then the K-long particle cannot, under any circumstances, decay into two pions. It just shouldn't happen, period. So what they did was actually pretty clever. They created this 57-foot-long beam of particles. By the time the particles got to the end of the beam, all the fast-decaying K-short particles had already vanished. That left them with a pure stream of just K-longs. All they had to do was sit back, watch, and see if any of them did the impossible. And after painstakingly sifting through 22,700 different decay events, they found them. 45 times they saw a K-long particle do the one thing it wasn't supposed to do, decay into two pions. 45 events that, according to everything they thought they knew, should never ever have happened. The evidence was just undeniable. This calculation right here shows how often this impossible decay happened. It's a tiny, tiny number, about 0.2%. But the most important thing about this number is that it's not zero. And in physics, finding a non-zero result for something that's supposed to be impossible, that changes everything. The perfect mirror of the universe was officially cracked. So, a tiny particle breaks a fundamental rule. You might be thinking, why is this such a big deal? Why did this win a Nobel Prize? Because that tiny imperfection, the one they found in a lab experiment, turns out to be the key to solving that enormous cosmic mystery we started with. What this CP violation really means is that the laws of physics aren't exactly the same for matter and for antimatter. It turns out nature has a slight bias. It plays favorites. It is a subtle, tiny, built-in preference for matter. You can literally see the final leap in logic right here in the researchers' own handwritten notes. This discovery breaks the asymmetry between particles and antiparticles. and also suggests that matter dominates over antimatter in the universe. That slight bias meant that way back in the early universe, for every billion antimatter particles, there were 1,000,000,001 matter particles. And after all the mutual destruction was over, only that one leftover particle in a billion survived. And that leftover stuff? Well, that's us. That's everything we see. So, what's the big takeaway from this whole cosmic detective story? First, the universe isn't perfect. Its laws have this tiny, but absolutely critical flaw. Second, that flaw is the only reason matter survived its war with antimatter. And finally, one of the biggest questions we can ask, why are we here, was basically answered by watching a very, very strange little particle misbehave. I mean, this discovery completely changed how we see reality. It showed us that even the laws we think are most sacred might have exceptions, and that the universe is way more interesting and complicated than we ever dreamed. It really just leaves you with this one fascinating question. What other cosmic laws are out there just waiting to be broken?